Welcome back to the Commercial Building Energy Auditing Procedures, Module 2. This is Part B. And in this module, we're going to continue on with some energy efficiency measures calculations, and then we're going to discuss what goes into an energy audit report. And there'll be a couple assignments associated with this module. Assignment 2B, you'll do another energy efficiency measure calculation for a furnace upgrade. And assignment 2C will be an assignment where you're going to put it all together and generate an audit report. For this module, we're going to talk about something called degree days, bin data analysis, and what goes into energy modeling simulation, and then the components of an energy audit report. In the last module, we looked at how to calculate the demand and the energy use for lighting. Lighting is a connected load. So it draws energy in terms of demand, which is watts or kW, and to get the kilowatt hours, the energy used over a period of time, we multiply the kW or the watts times the number of hours and we get kilowatt hours. So we have a demand, which is the connected load, and then we have a period of time that they're on. So if we were to calculate the energy used, we would take the watts times the number of hours that they're on, divide that by 1,000, and we would get kilowatt hours. The demand is simply the watts and divided by 1,000 to get kW. That's what's called the demand. We can look at fans and pumps in a similar fashion. The number of hours on and their connected load. But fans and pumps are generally given in terms of horsepower, 25 horsepower pump, 50 horsepower fan, etc. But we can convert from horsepower to kW. It's just a conversion factor of 1 horsepower is the same as 0.746 kW. And we can apply these similar types of calculations where we have the energy is kilowatt hours. We take the horsepower, multiply that by 0.746, and then multiply that times the hours on, and then the demand also is done in a similar manner. It's actually a little bit more complicated than that because fans and pumps, of course, have motor inefficiencies and fan inefficiencies, but that's beyond the scope of this module, and so I'm just going to leave it there because the concept is the same. And then the last thing to think about is the cost, and electricity is usually paid for in kilowatt hours, and so we had $1 per kilowatt hour, the energy cost, and oftentimes commercial facilities have to pay for their demand cost also in addition to the energy cost, and so there was $1 per kW. HVAC equipment is different, and it gets complicated fairly quickly. The demand or the load on the HVAC equipment is going to vary depending on what's happening outside. For instance, the heating load is going to increase as the outside air temperature decreases. And the cooling load is going to increase as the outside air temperature increases. And the utility companies, and we calculate heating load and, well, we'll talk about the specifics here, cooling load, generally in terms of BTUs per hour. The load is in BTUs per hour. And the energy used is in terms of BTUs. But utility companies don't bill in terms of BTUs straight up. They bill in terms of what the utility is using. For instance, natural gas is going to bill in terms of therms, a unit called therms. And electric equipment is going to get billed in terms of kilowatt hour. So depending on the type of equipment you have and what that equipment is doing and the type of energy it uses affects the units and the billing method for that. So let's talk about heating first. The heating load is, let's say, by conduction. That means the heat load that's transferred from the inside to the outside through the walls, windows, roof, etc. That's by conduction. And you don't have to remember this, I'm just doing this for illustration purposes. And the heating load, we'll call that Q, is dependent upon 3 things. First of all, the components that the conduction going through is made of. For instance, the walls are made of wood, insulation, some siding, etc. And we talk about that material for conduction in terms of something called its conductivity or its ability to conduct transfer heat. And it's the inverse of the resistance. So resistance is like the R value. And we calculate the R value based off of how much insulation it has, et cetera. And you may have had some instances where you've done that calculation. But the heating load, the heat loss, is the inverse of that R value, which we'll call the U value, times the surface area that we're conducting the heat across, say the surface area of the wall or the window, etc., and the temperature difference. Now, the U value is not likely to change over a period of time, and the area is not likely to change. But what will change, and the inside temperature when we're heating is likely to remain constant. Let's say we're heating to 68 degrees Fahrenheit. But as we can see, the outside air temperature changes all the time. Daily, it may start out at 0 degrees Fahrenheit and go all the way up to 30 on, say, a cold climate. And then it drops back down. So for over the period of a day, it's always changing. So when engineers design the size of a piece of heating equipment, whether it's a furnace, a boiler, a gas pack, whatever, what they do is they look at the inside temperature and then the outside temperature at a certain design outside temperature. And it's not the coldest it gets outside because then it would be oversized so much of the time, but it's pretty close. So they'll design the equipment so that it has the capacity to be able to meet the load at what they consider design conditions, which is, about as cold as it gets out there. And so let's look at the units now. The units for U value are BTU per hour, square foot, degree Fahrenheit. The units for area are square foot, and the units for the temperature is degree Fahrenheit. And when you put those all into this equation, what you get as Q comes out in terms of BTUs per hour. And that is the size of your HVAC equipment designed to meet the certain load. So that's how the engineers size the equipment. But once you have the equipment in place and you're going to run the equipment, then that equipment is going to use energy over a period of time. And that energy use is going to be that BTUs per hour with some inefficiencies calculated in, which I'll talk about soon, over a period of time. And so if you were looking at a day, you would say, okay, the BTUs per hour for hour 1 when it's 0 degrees outside is going to be a lot different than hour 12 when it's 30 degrees outside. You just do the math. And then you sum it up over that period of time. And it's constantly changing. So estimating the energy use when it's constantly changing every hour through a period of time, let's say a year, gets very complicated. Engineers have come up with different ways of dealing with this, and we're going to look at those. One of the ways is called the steady state calculation, and this is described on page 68 in the handbook. And the simplest method of these is called the degree day method. First, what is a degree day? Well, by definition, a degree day is 65 degrees Fahrenheit minus the average daily temperature for that day. And the average daily temperature for a single day is you take the low temperature of that day plus the high temperature of that day and you divide it by 2. So let's look at an example. Determine the degree days for 1 week in Eugene, Oregon. If out of 7 days, 1 week, 3 of those days have an average daily temperature of 45 degrees Fahrenheit and 4 days have an average daily temperature of 25 degrees Fahrenheit. And recall, the average daily temperature is the low temperature plus the high temperature divided by 2. So that's the average of 4 days and 3 days. So what you do is you have 65 minus 45 times 3 days, that's 60 degree days. And 65 minus 25 times 4 days is 160. So for that week in Eugene, you had 220 degree days. So I'll introduce the degree day method of estimating heating equipment energy use in a minute here, but I wanted to point out some things about degree days. First of all, the degree days mean that there's a base at which the building is neutral, and that's 65 degrees Fahrenheit. So at temperatures below 65 degrees Fahrenheit is when heating will occur, and above 65 degrees, no heating is required. And so it's kind of like that neutral or balance or steady state. And the heating load will vary depending upon the number of degree days that you have. And you could look at it in terms of years or days, and I'll show you that in a second. And of course, degree days vary by location. The number of degree days in Eugene, Oregon is going to be much greater than the degree days in, say, someplace in Florida, and probably less than someplace in Minnesota. So here's some examples of what you might find. The degree days for Eugene for a year, an average year might be 47.26. Boston, which gets pretty cold, 56.34 degree days. Orlando, Florida has 766, and Los Angeles is 1458. And what this means is that the heating equipment, the same furnace, the same gas pack, whatever you want, located in these different climates are going to consume energy to heat a space to the 65-degree baseline relative to their degree days. And there's a formula to estimate the heat loss in BTUs per year if we know the location and the degree days, and we know a little bit about our building. So the heat loss for a year, that's BTUs over a year, the heat loss, is based off of the overall average heat loss coefficient. That's the heat loss coefficient of averages of all of the building components. And this is the overall surface area of your building. And DD is the degree days for the location. And we have to multiply it by 24 because the way the units work out, degree days being in units of days. So let's do a quick example. Let's say we have a building in Milwaukee, Wisconsin, and it has an overall UA of 805.2 BTUs per hour degree Fahrenheit. We're not going to go into how to calculate the UA because it's just beyond the scope of our work here, but that's basically the overall U value times the overall surface area averages multiplied together. And let's calculate the estimated annual heat loss in BTUs per year. So we have this formula, UA times degree days times 24. 805.2 is given as our BTUs degree day Fahrenheit UA value. And degree days for Milwaukee is about 7635. Now the units of degree day are degree day. So if we do the math, we get a really big number. But BTUs are small, and so this is about 148 million BTUs in a year that is the heat loss of this building. So that's good to know, but what we really want to do, since we're energy auditors here, we want to know how much energy it's going to take to heat this building, and that depends on the type of equipment that we use. So let's assume we're going to heat this building with an 80% efficient natural gas furnace. So mathematically, the way we're going to do that is we're going to take this heat loss and divide it by 0.80, and that's going to be the energy input to heat this building with an 80% gas efficient furnace, and that comes out to this number here, 184,431,060. And again, that's in BTUs. Now, it's natural gas, and natural gas utilities do not bill off of direct BTUs. What they use is a therm. So the approximate energy that the owner of this building is going to pay for in a year is going to be 1844 therms. Again, that's in Milwaukee, Wisconsin. Now, if you took the same building and the same efficient furnace and located it in Eugene, Oregon, you would get less therms, and that makes sense because it's a milder climate. And if you needed to have a furnace in Orlando, Florida, highly unlikely. It would be even less than that. So that's the premise of estimating the energy use using the degree day method. Now, there's some things that are assumed here. First of all, the 65 degrees is assumed that that's where the neutral point is. And we're also assuming that the furnace is 80% efficient all the time. But for simple systems like this, those assumptions are okay. Also notice what would happen if I replace this 80% efficient furnace with a 90% efficient furnace. Then what I'll do is I'll divide this by 0.90, and this number is going to be smaller. It's going to be more efficient. And so that could be an energy efficient measure that you could calculate. Okay, so that leads us into assignment 2B. And in this one, you're going to calculate an energy efficiency measure by replacing an existing 80% efficient furnace with a 90% unit. The building is located in Portland, Oregon, and you're going to have a UA value of 960. And you're going to assume Portland has 5,000 degree days per year, and estimate the energy used for an 80% efficient furnace and a 90%, and you're going to calculate the energy cost savings, assuming $1.13 per therm for the cost of natural gas, and that the new unit costs $12,500. So you're going to calculate the energy savings in therms and MMBTU. The reason a lot of jurisdictions like the unit of MMBTU because, of course, the BTU is so small, so it makes the number a little bit more manageable. Therms is really just used for natural gas. And then you're going to calculate energy cost and the simple payback. I just walked you through the degree day method of estimating the energy use for heating equipment. And it's pretty useful, but in limited applications. First of all, it's very simple and easy to use, but it comes with some assumptions. One of those is that the efficiency is constant throughout the whole year, and it's best for heating applications. But the degree day method comes up short if you're trying to estimate the energy use of, say, a heat pump. A heat pump has different efficiencies depending on how cold it is outside on the heating side, and it also does cooling. Now, the degree day method has been used. There are some cooling degree day methodology out there, but it's not very common, and I didn't want to introduce it here. The next method, though, is something that's a little bit more practical and offers more flexibility, and that's the bin data method. The next method, which is a little bit more flexible, a little bit more accurate, is the bin data method, and that's described in the handbook on page 69. And basically that uses weather data in separate intervals or bins, and I'll show you in a moment how that's set up. But the hours per year are separated into 5-degree intervals, and then you use an Excel spreadsheet to do your calculations, and it's very flexible. Let me show you how that works. What the bin data method does is it takes hourly weather data in terms of months, so this is January, February, March, April, May. This weather data is downloaded from Weather Data Information online, and this is for a location near Oregon State University called Philomath. And here are the temperature ranges from 20 to 25 degrees, a range of 5-degree intervals, and 100 to 105. And basically what it's saying is that in the month of January, there are no hours that the temperature is in this range. But there are 94 hours that the temperature is in the range of 40 to 45 degrees. So this is basically the whole year divided up into 5-degree intervals and how many hours it exists in those temperature ranges. But it's also a little bit more refined than that because we set this up in Excel, and so we did the temperature step in 5 degrees, but also we looked at the time range. We said it's from 7 a.m. to 6 p.m. And what we were doing is we were looking at a school. Now, I'm not going to have you do bin data analysis because it gets kind of complicated and you need to know a fair amount about Excel and also a fair amount about your HVAC equipment. But what I do want to point out is that it's kind of powerful in that you can set up an Excel spreadsheet and you can do both cooling and heating in the same spreadsheet. And so you can sum them up and you can do the cost. You can do a lot of work here, and you're not doing a full-blown energy model simulation. You can break your energy efficiency measures down into different components and look at them in a lot more detail. It's very practical, and engineers use this a lot. Again, doing that is beyond the scope of this course, but I wanted to give you a little more detail than what the handbook does about what the bin data is and its practicality. And the last methodology that I want to talk about is, of course, the energy model / simulation. Some of you may already be familiar with this. eQuest is a program that's developed by the Department of Energy that's used extensively by energy auditing engineers. And basically, it's a program that's set up to run all of the information on your facility for every hour of a typical year. So that's 8760 calculations, and it calculates everything for every hour of a typical year. It estimates the whole building energy use, but it also estimates where that energy goes, whether it goes into cooling or heating or lights or fans. It will break that down for you. It has a complex input, but also a very detailed output. This is generally reserved for level 3 energy audits. Well, I'm going to have to stop this video here. There's going to be one more video in this series, and that's on the report writing.